Hello, everybody. This is Dr. Weber, and this is your mini lecture about current. Now, let me share my PowerPoint screen with you. And this image here is a bunch of different resistors. If we remember from lab, our resistors have color codes, color bands on the side that tell us what the amount of resistance is for each particular resistor. So the electric current, which we have also seen in lab already, is the rate at which charge flows. And here's the equation for current, one equation for current. Current is defined as the capital letter I, and that equals to the amount of charge that can flow through a cross-sectional area per unit time. So here we have charge flowing through a cross-sectional area. And the units of charge the units of current are units of amperes. 1 ampere is equal to 1 coulomb per second. Okay, so if you watch the crash course video about current, you will know a few of these things that I'm already talking about here. But we choose a particular direction for what we call the conventional current. And this current, this flow of charge, flows from high voltage to low voltage. And I forgot to mention to you, behind me, I have some current flowing. This is water flowing over the edge of one part of the Niagara Falls. And just like how water has current, we can think about electric current as being a flow of charge. And just like how the water flows from regions of high gravitational potential energy to regions of low gravitational potential energy, our current flows from high voltage to regions of low voltage. Okay, and our current flows from the positive end of our battery, or the positive terminal of our battery, to the negative terminal of the battery. And so here is a schematic of how we might have a circuit diagram. And we've got our battery here. We've got the positive terminal represented by the longer line here, our negative terminal represented by the shorter line here. Our current is flowing from this positive terminal around our circuit to the negative terminal. This symbol represents a resistor, which we will talk about later, and this current in this particular diagram is flowing clockwise, the direction of a clock. Now, up here is the same idea. Down here was the schematic. Up here we have the actual thing in real life. We've got, let's say, a car battery. We've got current moving through the wires to light up a headlight, and then that current flows to the negative end of the terminal. Now, this flow of current is opposite the direction that negative charges move. So really, when we're talking about current, we're talking about the flow, or the direction in which positive charges would flow within our circuit. Now, the flow of positive charges in one direction is equivalent to the flow of negative charges in the opposite direction. So why do we choose the particular direction that we do for current when it's really the electrons that are the charge carriers? Well, we can thank Benjamin Franklin for that. And if you watch the crash course video about current, you will learn more about Benjamin Franklin and why we choose current in the direction that we choose it to be now in modern physics. Okay, ooh, I have to move my picture again. So electric signals travel at speeds on the order of 10 to the 8 meters per second. So this is a significant fraction, pretty close to the speed of light. Remember that the speed of light is 3 times 10 to the 8 meters per second. So how fast do the particles move inside our wires? Our particles, our electrons that are, or our charges that are moving inside our wires that create the current, the electric current that we're talking about. How fast do they move? The actual, what we call the drift velocity of the electrons is only about 10 to the minus 4 meters per second. So that seems pretty small, right? So our charge carriers take something like a random walk inside the wire, the conductor, but with some particular direction in mind. And so our electron here, our charge carrier, is bouncing around inside the conducting wire here. The sharp changes in its direction here are due to collisions with other atoms inside the conductor. So even though it takes something a little bit like a random walk, in general, the net motion of these electrons is going to be in one particular direction. And we note that the net motion of our electrons here is opposite the direction of the electric field inside the conductor and opposite the direction of this current too. So on an order of about 10 to the minus 4 meters per second, these electrons, these charge carriers, are still on average moving about 10 to the minus 4 meters per second in the direction opposite the conventional direction that we call the current. Now, our current depends on the average speed of charge carriers, the number of these charge carriers per unit volume, and the size of the charge carried by each of our charge carriers. So here we have an equation that shows the amount of, like the rate of change of charge, and that is equal to this whole quantity here, which represents the number of mobile charge carriers per unit volume. That means the number of charge carriers per unit volume that are free to move around, free electrons essentially. And that number is equal to the number of our electrons times some volume. So we've got our area here, cross-sectional area of our wire, times delta x, some distance x, okay? So our cross-sectional area times some length, so we're essentially sweeping out a volume of a cylinder here, and then we multiply that by q, okay? And so we remember that our distance, or our change in distance, is equal to some velocity times time. And so we can replace our delta x here with a drift speed or drift velocity times time, since x is equal to v times t. So here we replace delta x with v drift speed times time right in here, and then we can get a new equation here. And so q is equal to n. This is our number of charge carriers times cross-sectional area times drift speed times time times the charge of our charge carriers. Now, we can rearrange this, and we remember that current is equal to the change in the amount of charge per unit area over time. And so we can solve this equation here. If we say that I is equal to delta Q over delta T, then I has to equal our number of carriers times charge times the drift speed times our cross-sectional area A. Okay, and we're going to use this equation in order to solve a problem that I will work through next. And here is the problem. I'm just going to set it up for you here with this slide. We have a copper wire of cross-sectional area 3 times 10 to the minus 6 meters squared, and it carries a current of 10 amps. We know that the density of copper is 8.92 grams per cubic centimeter, and its atomic mass is 63.5 atomic mass units. So assuming that each copper atom contributes 1 free electron to the metal, we want to find the drift speed of the electrons in this wire. So here's the answer. We will go through it next. And then for part B, we're going to use the ideal gas model to compare this very small drift speed with the random RMS, or root mean squared speed of an electron that we would have at 20 degrees Celsius. And to do this part, we have to go back all the way last semester towards the end, remember all of our work about thermodynamics. Okay, so we are going to calculate a drift speed and compare it to the RMS, or the root mean squared speed of an electron gas. So we have a copper wire that has a cross-sectional area of 3 × 10⁻⁶ meters squared, and it carries a current of 10 amps. So we're going to assume that each copper atom contributes 1 free electron to the metal. And with that, we're going to find the drift speed of the electrons in this wire. So if we think about our equation for current, one way we can write the current is by saying that the current is equal to N times Q times the drift velocity times A. So in this equation, N right here is the number of charge carriers per unit volume inside our material. Q here is the charge per charge carrier. So in this case, that's our electron. V, that's our drift velocity, and A here, that's the cross-sectional area of our wire. So we're looking for the drift velocity. I can solve this equation for drift velocity. So the drift velocity is equal to the current divided by our number of charge carriers times Q times A. Okay, so we know the current, we know the cross-sectional area, we know Q, but what are we going to use for N here? The number of charge carriers per unit volume. To do that, we're going to start by figuring out what is the volume of our of 1 mole of copper. And so we can do that by saying that the volume of 1 mole of copper, so remind ourselves that this is 1 mole, is equal to the mass of 1 mole of copper divided by the density of copper, okay? And so we look on the periodic table and we can find the atomic mass of copper from the periodic table. And from that we know that 1 mole of copper is equal to 63.5 grams per mole, okay? And also something that I'd have to look up, the density of copper is 8.92 grams per cubic centimeter. So we've got 8.92 grams per cubic centimeter, okay? And then I see here that my grams cancel here and here, and so I divide those two, and I'm left with that the volume of 1 mole of copper is 7.12 centimeters cubed, okay? But I want to get this in standard units of meters cubed. So we got to change our centimeters cubed to meters cubed, all right? So to do that, I have that 7.12 centimeters cubed. In order to change that from centimeters cubed to meters cubed, I can use a conversion factor. So in 1 meter cubed, I know that there's 100 centimeters cubed, okay? So I'm going to take 7.12 and divide it by 100 cubed in order to get centimeters cubed into meters cubed. And so if I do that, I find that the volume of 1 mole of copper is going to be 7.12 times 10 to the minus 6 meters cubed. So remember, that's just volume of 1 mole of copper. Okay, now we've got to get the number of our charge carriers, or our number of electrons inside this volume, okay? And so in order to do that, I will use the following. So my number of electrons per volume, or charge carriers per volume, is going to equal to our number of electrons per mole divided by the volume of our copper per mole, okay? So our number of electrons per mole, that's just Avogadro's number, okay? And so that's going to be 6.02 times 10 to the 23 electrons per mole. And I'm going to divide that by this value that we just found right here, 7.12 times 10 to the minus 6 meters cubed per mole. Okay? And so my units here of moles are going to cancel. And if I take 6.02 times 10 to the 23, divide it by 7.12 times 10 to the minus 6, I find that we have 8.46 times 10 to the 28 electrons per meter cubed in our copper wire. So now I just found the volume, or the value here for N, and so now I can calculate my drift velocity. So I'm running out of room here. Let's take our drift velocity and rewrite it right here. So our drift velocity, or our drift speed, is going to be equal to our current, which is 10 amps. And I'm going to divide that by my number of charge carriers per unit volume. So that's going to be 8.46 times 10 to the 28 electrons per meter cubed. And then I'm going to multiply that by the charge of my charge carrier. And so that's our the charge of our charge carrier. That's our electron. That's the 1.6 times 10 to the minus 19 coulombs. And then my cross-sectional area, which was given to us here, we've got 3 times 10 to the minus 6 meters squared is the cross-sectional area of our wire. Okay. So then, 10 amps divided by all of these quantities multiplied together, we find that the drift velocity is equal to 2.46 times 10 to the minus 4 meters per second. We're going to use the ideal gas model to compare this drift speed with the random RMS, or root mean squared speed of an electron that an electron would have at nearly room temperature at about 20 degrees Celsius. So we need to find the RMS speed of a gas of electrons at 20 degrees Celsius. This is way back last semester from our section on thermodynamics. And from there, we learned that the RMS, or root mean squared speed of a species of gas, if we think about them as being an ideal gas, is equal to 3 times the Boltzmann constant times its temperature divided by the mass of that species, all of that square rooted. Okay? So Kb, that's our Boltzmann constant. M, that's the mass of our individual particle. T will be our temperature in degrees Kelvin. Okay? So this is going to be equal to 3 times our Boltzmann constant, which was 1.38, times 10 to the minus 23 joules per Kelvin. And then we have to multiply that by our temperature in Kelvin. So we're told that our gas is at a temperature of 20 degrees Celsius. To get that into Kelvin, we take 273 plus 20. So our temperature in Kelvin will be 273 plus 20. Okay? And then that's all divided by the mass of our electron, which is 9.11 times 10 to the minus 31 kilograms. And then we square root all of that. And so then we find that the root mean squared speed of an electron gas would be 1.15 times 10 to the 5 meters per second. So that's much larger than our drift velocity, or drift speed right here. And actually, if I go ahead and compare them, if I divide our RMS velocity over our drift speed, I find that the RMS velocity is 4.68 times 10 to the 8 times larger than our drift speed. Okay, so much, much faster. So our drift speed in our electron in a wire is very, very small, only about 1/1000th its random thermal speed. So why is it that an electric signal seems to move so fast when we flip a light switch? we can think of our analogy of current as like a flow of water through a pipe. Okay, so here I have my pipe, and let's say that this pipe is already filled with water, or in our case, it's already filled with some free electrons inside here. And so if we force one drop of water into the end here, a drop must be pushed out on the other side, assuming that we have conservation of mass, or that our fluid, in this case, would be incompressible. So in a conductor, the electric field driving the travel of free electrons travels at about the speed of light. So when you flip on the switch, the message for our electrons to start moving reaches them at about a speed of 10 to the 8 meters per second. Not quite, but pretty close to the speed of light. Now, in the problem that I just solved, you'll notice that I found a speed, not a velocity. So I didn't take into account the negative charge of our electron. And so if I were to do that, if I were to say that Q is equal to minus 1.6 times 10 to the minus 19 coulombs, our answer for our drift velocity would actually be negative. And in fact, our drift velocity is actually opposite the direction of conventional current. So if I'm talking about drift velocity, then the answer really should have been negative. But if I'm thinking about drift speeds, remember speed has no direction, but it has a magnitude, then I would be reporting my value with a positive number. Now I know that I'm not always careful about the difference between drift speed and drift velocity, but really the drift velocity is negative because it's opposite the direction of conventional current.